Now we're going to look at solving trig equations using adjusted interval methods. To solve using adjusted interval methods, you're going to use this method when there is a multiple of an angle inside of a trig function. And what we mean by that is you're going to have inside of the trig function some number n times theta. Our first step will be to isolate the trig function. Here we have sine of the input angle, and we notice that input angle is some number times theta, so that is what we would call the multiple of an angle. On the other side of the equal sign, we have the ratio. So our first step will be to get the trig function by itself on one side and then the ratio on the other. So step one for us in this example is already done. Okay, let's look at step two. Step 2 says we're going to solve for all angle solutions of the multiple of the angle in an adjusted interval. Okay, so let's look at what we're solving and kind of break some things down. First off, we're given sine of 2 theta. Remember, we're asked to solve for theta is equal to the square root of 3 over 2. You got that. And we're given this interval. Something that's really important to understand about the interval is that this is the interval for which you're supposed to find solutions for theta. So we're asked to find all possible solutions for theta between 0 and 2 pi. Let's break this down again too. What that's saying is that our solutions can include 0. That's what the bracket means, included. So theta is in between 0 and including 0 and 2 pi. So 2 pi here. This means included. So when you see the bracket, that means included. And this means not included. And that comes from over here, the parentheses. Alright, so the given interval is what we're asked to give our final answer for theta after we finish solving the equation completely. Alright, so step 2 says we're going to solve for the multiple of the angle, so we're actually going to solve for 2 theta. So I'm going to say 2 theta is equal to what? Now we're asked to solve for 2 theta, all of those angles for 2 theta within an adjusted interval. So how do we get this adjusted interval? The adjusted interval comes from taking the original interval that we are given, which is here. I used A and B as kind of placeholders. But we're going to take that given interval and we're going to multiply through by whatever number was in front of theta. So we're going to multiply the first number by n and the second number by n. Okay, what does it look like in this example? Well, in this example we have 2 theta, right? We're asked to solve for theta within this interval from 0 to 2 pi. So what we're going to do is we're going to adjust this interval by multiplying all the parts by 2, the number that's in front of theta. Alright, so that means I'm going to take this interval, if you want to think of it like that, we're going to multiply through by 2. 2 times 0 is 0. 2 times theta is 2 theta. 2 times 2 pi is 4 pi. Alright, so that means the interval that we're actually going to be solving then for 2 theta is actually 2 times 0, which is 0, 2 times 2 pi, which is 4 pi. Alright, so step 2 is saying to solve for that multiple of that angle within the adjusted interval. Alright, so let's see what that looks like. First thing we want to do is we want to think back to the ratio. So our ratio is a positive ratio, square root of 3 over 2. So in order to solve, we still have to do quadrant check and reference angle family. Quadrant check, we're looking at a positive ratio for sine, so that's going to come from quadrants 1 and quadrants 2. So there's our quadrant check. What's our reference angle family? So think back to your unit circle. Alright, we want to think about what points are going to have a second coordinate of the square root of 3 over 2. Is that the pi over 3 family, the pi over 4 family, or the pi over 6 family, or is that one of the quadrantal angles? So you want to know your unit circle well enough to know that that represents actually the pi over 3 reference angle family. So here we have pi over 3 from quadrant 1. Okay, what about quadrant 2? Is that our 2 pi over 3? So we have pi over 3 from quadrant 1 and then 2 pi over 3 from quadrant 2. Now the key for this, and where we have to kind of keep going back to, is that we're asked to solve for 2 theta within the given interval 0 to 4 pi. Now that's not just one time around the circle, right? That's twice around the circle. So in order to capture all possible solutions for 2 times around the circle, we need to find coterminal angles. Okay, so we're going to be looking for coterminal angles to the 2 we've already found. So the 2 that we already found are from one time around the circle. We want to find 2 more that comes from the second time around the circle. So we're going to find coterminal angles to the 2 we've already found. Alright, to find coterminal angles, we add 2 pi. We're going to think about that as 2 pi over 1. We'll give a common denominator of 3. So we have pi over 3 plus 6 pi over 3. And that gives me 7 pi over 3. So I'm going to add that to our list. So that's a coterminal angle for the second time around to that quadrant 1 solution. Alright, we have to do the same thing for our quadrant 2 angle. I want to add 2 pi. Okay, so 2 pi over 1, we're going to add that to the 2 pi over 3. I have to have a common denominator of 3. So I'm really adding, what is that, 6 pi over 3 plus 2 pi over 3. So that quadrant 2 angle, I get 8 pi over 3. Okay, so step 2 says to solve for the multiple of that angle within the adjusted interval. So in this case, when we adjusted our interval, we had to solve for angles between 0 and 4 pi. That's 2 times around the circle. We found our first 2 angles, but then to find the second 2 angles, we had to find coterminal angles to the original 2. Alright, so step 3 says that we're going to take all of the angles that we found in step 2, and now we're going to solve for theta. So right now we have that 2 theta is equal to these 4 angles. We're going to solve for theta by dividing both sides by whatever number is in front of theta. So I'm going to divide all of the angles on both sides by 2. Now, instead of dividing everything through by 2, because you notice that looks pretty ugly, we end up getting a pretty ugly fraction, we're going to think about, in this case, of multiplying by the reciprocal, and that'll just make the calculation look a little easier. So I'm going to multiply on both sides by the reciprocal 1/2. Now, when I do that on the left-hand side, we get just theta. So all of that cancels out. Now I'm going to do that on the right-hand side to all of the angles. So I'm going to multiply each one of those by 1/2. Okay, so when I multiply fractions, you do top times the top, bottom times the bottom. 1 times pi is pi. I'm going to do 2 times 3, that gives us 6. So essentially what happens here is that the tops of all the fractions are going to stay the same, and the bottoms get multiplied by 2. Now, before we say that we're done and we have our answers, we always like to reduce the fractions. If there's any common factors, we always like to reduce those fractions. The first one is pi over 6, can't reduce that. The second fraction, 2 and 6, have a common factor. So let's cancel those common factors. Divide here by 2, divide here by 2. I get pi over 3. 7 pi over 6 is reduced as much as possible already. The third fraction, we have a common factor of 2 again, so I can divide the top and the bottom by 2. I get 4 pi and divided by 3. All right, so our final answers for theta are those 4 angles, and you'll notice that all 4 of those angles now fit within the interval that we were asked to solve for theta originally, between 0 and 2 pi. All right, so our final answer, all 4 of those angles there in green. All right, for this next example, we're looking to solve cosine of theta divided by 2 is equal to the square root of 2 over 2. The interval that we're given is between negative pi to pi. We want to remember that this is the interval for which we are asked to find solutions for theta. So we're finding all possible solutions for theta within the given interval. Step 1 is to make sure the trig function is isolated. It is by itself on one side, and that step is already done. Step 2 for adjusted interval methods is to solve for the multiple of the angle. So we're going to solve for theta divided by 2. Now we're going to adjust our interval. We want to multiply or divide by theta throughout that interval by whatever is being multiplied or divided by theta inside of the trig function. So that means that to adjust this interval, I'm going to go through and I'm going to divide everything on both sides by 2. So that means I'm solving for theta divided by 2 between negative pi over 2 and pi over 2. So this is what we would call our adjusted interval. Alright, so we still have to do quadrant check. And reference angle family. Alright, our ratio is a positive square root of 2 over 2, so that's quadrant 1 and quadrant 4. Alright, so we'll think back to our unit circle. Okay, what is our reference angle family? What angles have a cosine ratio of square root of 2 over 2? That would be, was that pi over 4? So you want to make sure that you're familiar with your unit circle and the angles. So it's pi over 4 from quadrant 1. What would that be? 7 pi over 4 from quadrant 4. Alright, so we want to be careful about something as we represent these angles. Our goal is to have the angles fit within the given interval. So here's our adjusted interval. We are looking for angles between pi over 2, so pi over 2 would be, from 0 to pi over 2 would be quadrant 1 in the positive direction. Okay. But then we're asked to think of the angles from quadrant 4 in the negative sense. So think about starting at 0 and then going in the negative direction, so that clockwise movement. So we're kind of going backwards from 0 to get to negative pi over 2. So essentially we have to think about all the angles that come from quadrant 1 as being positive, but all the angles that come from quadrant 4 as being negative. So positive angles in quadrant 1, negative angles in quadrant 2. So I'm going to say that pi over 4 is perfectly fine. That's a positive angle from quadrant 1. But how do we think about 7 pi over 4 in the negative sense? Well, I'm going to start at 0, and I'm going to go back in that negative direction, pi over 4 units. So that's actually going to be negative pi over 4. In other words, what we want is a negative coterminal angle. So instead of having 7 pi over 4, we wanted a negative coterminal angle. Now, what's another way that you could come up with negative pi over 4? Remember, we find coterminal angles by adding or subtracting 2 pi. So I could think about subtracting 2 pi. Think about that as 2 pi over 1. We need a common denominator of 4. So that would be 7 pi over 4 minus 8 pi over 4. And that gives you negative pi over 4. So our quadrant 4 angle, we're actually going to have negative pi over 4. Alright, and those turn out to be the only two possible solutions that we could find within the given interval. So we'll move on to step 3. Step 3, we're going to take all of the angles that we got from step 2, and we want to solve for theta. So I want to get theta by itself on one side. So in order to get theta alone, on the left-hand side I'm dividing by 2, so I'm going to do the opposite. I'm going to multiply by 2. We're going to do that on both sides. So on the left-hand side, the 2's cancel, end up with theta. And I'm going to multiply top times the top. So I get 2 times pi is 2 pi. Bottom times the bottom. So that's 4. Then I'm going to do the same thing to everything. So I'm going to multiply by negative pi times 2, and I get negative 2 pi over 4. And before I decide those are my final answer, we always reduce our fractions. So I have a common factor of 2 there. Divide the top and the bottom by 2. I get pi over 2. Second fraction also has common factors, so I'm going to divide top and the bottom by 2 there as well. I get negative pi over 2. Alright, so these are our final two solutions for theta. And you'll notice that these solutions fit within the original given interval that we were asked to find all possible solutions for theta. Here we're looking to solve tangent of 3x is equal to 1. The given interval is from 0 to 2 pi. Before we start, we notice that we have a multiple of an angle inside. So we have 3 times x. So we're going to use adjusted interval methods to solve. Our goal is to solve for x by itself. The given interval for which we are going to solve for x is between 0 and 2 pi. So our final answer, all of our solutions must be between 0 and 2 pi. Alright, so step number 1, we need to get the trig function by itself on one side. So we're going to isolate the trig function, and that's actually already done for us. Okay, for step 2, we are going to solve for the multiple angle that's inside, but we have to do it within an adjusted interval. Okay, so for the adjusted interval, we are going to take the given interval for x between 0 and 2 pi, and what we're going to do is we're going to multiply everything by the number that's in front of x. So I'm going to multiply through by 3. So the adjusted interval, we're going to solve for 3x between 3 times 0 is 0, 3 times 2 pi is 6 pi. Alright, so in order to solve for the angles, we have to do quadrant check. And then we also need to know what is the reference angle family. Alright, quadrant check, we have a positive ratio of 1. Let's see, tangent is positive in quadrant 1 and then quadrant 3. Our reference angle family, if we're familiar with the unit circle, whereas tangent have a value of positive 1, And that would come from the, what is that, the pi over 4 family. Alright, so make sure you're familiar with that unit circle. So pi over 4 from quadrant 1, and what is this? 5 pi over 4 from quadrant 3. Alright, so those are our angles. Alright, let's go ahead and copy those down. For quadrant 1, pi over 4. Quadrant 2, sorry, from quadrant 3, 5 pi over 4. Now we need to go back to, we're solving for 3x right now in the adjusted interval. Since we multiplied by 3, what we're basically doing is we're looking for angles for 3 times around the circle. So pi over 4 and 5 pi over 4 are for 1 time around the circle. We need to go around the circle again. We need to find coterminal angles to the quadrants 1 and 3 angles that we've already found. We need to do that once, but then we need to do it again. So this is for the second time around the circle, but then we're going to do it again. We're going to find coterminal angles for the third time around the circle. Okay, so for the first time around the circle, we found pi over 4 and 5 pi over 4. We're going to find coterminal angles to those. Thinking about it like this, so we don't stop at pi over 4, we go all the way around, and we're going to stop after one complete rotation. We're going to stop at that same place. That's adding 2 pi. Okay, so that means I need a common denominator of 4. So pi over 4 plus 8 pi over 4. So for the second time around into quadrant 1, I get 9 pi over 4. So I'm going to put that right here, 9 pi over 4. Alright, let's do the same thing for 5 pi over 4. Thinking about this again as going all the way around. I'll do this one in green. Going all the way around and not stopping at 5 pi over 4, but doing one more full complete rotation and stopping here on the second time around the circle. Once again, to find coterminal angles for a second time around, we add 2 pi. We need a common denominator of 4, so that's 8 pi over 4 plus 5 pi over 4, and that gives us a total of 13 pi over 4. Okay, we're going to add that to our list. Alright, so both of those angles are for the second time around, but between 0 and 6 pi means we need to go 3 times around the circle, so we're going to add 2 pi again. So I'm going to take the two angles that we just found, those coterminal angles, and we're going to add 2 pi to those. Okay, so this is for the second time around the circle. If we add 2 pi, we're going to get an angle for the third time around the circle. Need a common denominator of 4. So I have 9 pi over 4 plus now 8 pi over 4, and I end up with 17 pi over 4. So that's for the third time around that unit circle. Remember, looking for coterminal angles, and we add 2 pi to find coterminal angles. Okay, we have one more to do. We're going to add 2 pi to 13 pi over 4. This is for the second time around the circle. We're going to add 2 pi to that angle to find the third time around the circle. So coterminal angle for a third time around the circle. 13 pi over 4 plus 8 pi over 4 again. We end up with 21 pi over 4. Alright, so our third step is to take all of the angles that we just found Okay, and we are going to solve for x. So on both sides, I either want to divide by 3. Now if I divide by 3 on everything, I end up with this really ugly looking fraction for all of them. So instead of dividing by 3 to get rid of the number in front of x to solve for x, I am going to multiply by the reciprocal on both sides. So I'm going to multiply here by the reciprocal, and then all of these fractions also multiply by 1/3. Okay, so on the left side, the 3's cancel. I'm left with 1x, or just x, which is exactly what I want. On the right side, I'm going to multiply every one of these fractions on the top by 1 and on the bottom by 3. It's going to leave the tops the same, but it's going to multiply all those 4's by 3, so I'm going to get 12 for every denominator. Alright, and then the last thing we always do is we always reduce our fractions. So if there's a common factor, at the top or the bottom, then we will divide out by that common factor. Let's see, 9 and 12, those are both divisible by 3, so I get 3 pi over 4. And 21 and 12 are also both divisible by 3, so I get 7 pi over 4. Alright, so this is our final answer. And all of these angles are going to fit within the original given interval for x between 0 and 2 pi. Alright, this last trig equation that we look at is probably going to be the most challenging. The first place that we're going to start is just looking at our equation, and we're going to notice that we have sine of 2x, so 2x represents the input angle. We have a sine squared, and then we have a sine, but they're both sine of 2x. So we're going to think about the algebra. We want to isolate the trig function. So we're going to let every trig function and its input angle be represented by an algebraic variable. So the algebra that we actually have then is 2 times w squared minus w minus 1 equals 0. Now, the first thing that I always tried is to see if it could factor. And if it factors, then it's much easier. If you don't remember how to factor, or if it can't factor, then you can always use the quadratic formula. Factoring is usually the easiest if you can remember how to factor. So I'm going to factor this. I'm going to set up 2 parentheses. 2w times w will give me 2w squared. I need opposite signs, so let's do plus and minus. And the only thing that can multiply together, last times the last, to give me a -1 would be a +1 and a -1. Alright, you can check that and make sure that that is the correct factorization. And I'm going to set each one of those factors equal to 0. Solve for w. I get w is equal to a -1/2 and w is equal to a +1. We want to go back to, what does w represent? W represents sine of 2x. So I'm going to replace the w's with sine of 2x. Alright, now we have two different little equations to solve. We're going to go back to our steps. First of all, we notice that we have multiple of an angle for both. If we have multiple angles, first thing I'm going to do is just verify, do we have the trig function by itself on one side and a ratio on the other? And we do for both, so step 1 is done. Step 2 for multiple angle equations, when we're solving using that adjusted interval method, is to solve for the multiple angle. So we're going to solve both of these for 2x. But another requirement here is to solve within the adjusted interval. So the original interval that we were asked to solve for x in, so remember this is just for x, is negative pi to pi. So we want to solve for 2x for both, so we're going to multiply through every quantity by 2. Alright, so our adjusted interval to solve for 2x then is negative 2 pi to positive 2 pi. Alright. Alright, let's look at the first one here. Sine of 2x equals to negative 1/2. We need quadrant check. The ratio is negative. Sine is negative in quadrant 3 and quadrant 4. Quadrant check. Reference angle family. Our reference angle, what quantity on our unit circle has a sine ratio of 1/2? I believe that's our pi over 6 reference angle family. Now remember, what we want is quadrant 3 and quadrant 4 was that 7 pi over 6 and 11 pi over 6. Okay. Alright, so we want to be careful again that we find all possible angles within the given interval. The interval that we're given is pretty different. Negative 2 pi to positive 2 pi. Now remember, right in the middle of those two is 0. So 0 radians to 2 pi, that's one time around the circle in the positive direction. So what that means is when I pick up that quadrant 3 angle, going in the positive direction, that's 7 pi over 6, so that's a solution I'm going to keep. And then I pick up 11 pi over 6, which is another solution we want to keep. Now, going backwards from 0, so going in this direction, these angles would all be negative. So these are all the angles that I get when I go in the opposite direction around the unit circle. So if I go in the negative direction, that hits right here. I get this quadrant 4 angle. What is that? That's a coterminal angle to 11 pi over 6, but it's a negative coterminal angle. So all of these angles are coterminal, but they are negative angles. Coterminal negative angles. How do we find coterminal negative angles? Well, we subtract 2 pi. So I'm going to think about that as 2 pi over 1. We need a common denominator of 6. Okay, so that's really 11 pi over 6 minus 12 pi over 6. So we get negative pi over 6. So that is a negative coterminal angle from going backwards around the unit circle, one full rotation. So I'm going to add negative pi over 6 also to the list. Okay, now that's the quadrant 4 negative coterminal angle, but I also need to get the quadrant 3 negative coterminal angle. So what about 7 pi over 6? Alright, so 7 pi over 6, we're also going to subtract 2 pi from that. Need a common denominator of 6. So I get 7 pi over 6 minus 12 pi over 6. Does it give us negative 5 pi over 6? All right, so our goal, once again, is to find all possible solutions for all the angles for 2x within the given interval. Negative 2 pi to 2 pi is going forward one full rotation in the positive direction, picking up all of those angles from quadrants 3 and 4 there, but then also going backwards one complete rotation to pick up all the negative coterminal angles also from quadrant 3 and quadrant 4. Alright, now step 3 for this is to take all of those solutions that you found in step 2 and we want to multiply by the reciprocal of 2. So I'm going to multiply both sides by 1/2. So here we are solving for x. I want to get x by itself, so we're getting rid of that 2. So we get x equals, I'm going to multiply the tops by 1 and all the bottom of those fractions by 2, so all the denominators are going to become 12. Alright, so that's what we get for the first equation. Now let's go to the second equation. We have sine of 2x is equal to 1, and we're solving for 2x first. Alright, so the ratio is 1. We want to figure out, okay, based on our unit circle, where do we have a sine ratio of positive 1? And that's up here at, what's that, pi over 2. That's a quadrantal angle, so we don't have a reference angle family to think about. So we get pi over 2. Now I want to make sure that before we give our answer that we're going within the adjusted interval. So we have to go forward in the positive direction, one complete rotation, and pick up all possible solutions in the positive direction. So pi over 2 fits in that. But then we also have to go in the negative direction. So I have to go all the way around the circle, starting at 0 and going in the negative direction, and also pick up all possible solutions along the way. So we actually pick up pi over 2 again, but since we're going in the negative direction, it's a negative coterminal angle to pi over 2. So we're going to subtract 2 pi to find that negative coterminal angle. Alright, so we're going to multiply top and the bottom by 2 to give those fractions a common denominator. I'll finish it down here. Pi over 2 minus, is that 4 pi over 2? Pi minus 4 pi gives me negative 3 pi, so I get negative 3 pi over 2. So a coterminal solution in the negative direction would be negative 3 pi over 2. Alright, so for that second equation, we get 2x is equal to pi over 2 and negative 3 pi over 2. Step 3 for that would be to take the equation that you have above, and we're going to multiply both sides by, again, 1/2. We want to get x by itself. So we get x is equal to, multiply the tops of each fraction by 1 and the bottoms by 2. So the denominators turn out to be 4. And for this equation, we actually end up with 6 solutions. 7 pi over 12, 11 pi over 12, negative pi over 12, negative 5 pi over 12, and then also pi over 4 and negative 3 pi over 4. All of these solutions now fit within the original given interval of negative pi to pi for x.